This webinar is about lysimeter techniques and the unique feature of the Smart Field Lysimeters. Thanks Decagon Devices for the invitation to give this presentation. The Smart Field Lysimeters have been developed together with them, with the Lysimeter Research Group and with the University of Prague. What is the problem of gravimetric lysimeters and how to reach true field situation inside lysimeters? Why and when do we use them and how do they work? What are their limits? This seminar takes about 45 minutes. Please feel free to ask your questions. I'll try to answer them after the presentation. Now, viable lysimeters are precision tools for water flux and water situations and water measurements in soils and their interfaces to the atmosphere and to the groundwater. This schematic overview shows the most important water parameters. These should be taken into account to solve the water balance formula. The unique power of lysimeters compared to other instruments is that they are working with soil surface and soil directly as a part of the instruments or setup. As we measure substances in concentrations in samples, taken for example with suction cups in different levels or in the drainage water, of course we need the mass transport information of the water balance for the determination of the substance fluxes. The overview indicates the wide field of applications too. It measures the atmospheric parameters like precipitation and evapotranspiration. Due to the high precision weighing system, we can measure all precipitation parameters like rain, snow, hail, dew or hoarfrost with a resolution of 0.01 millimeter. Also, it measures the lower boundary or output as drainage, or inversely the capillary water in the depth of the lysimeter bottom. Therefore, we use smart field lysimeters for water suppliers and hydrologic research as they give both information, atmospheric input directly and the continuously changing soil surface and groundwater recharge capability. They also work at sites with a negative water balance, which means evaporation is higher than precipitation. We may use them for climate change projects. The climate feedback concept developed by the KIT IFU Institute in Garmisch-Partenkirchen. For climate change experiments, we move soil from a colder site to a warmer site and compare several lysimeters among each other. We measure the climatic parameters with weather station to protocol at which change climate parameters microcosms react different. Which species will be dominant at new conditions? How does CO2 and respiration change? How does the water balance change? Soil science applications vary over a wide range, but most questions are influenced by water. Lysimeters offer defined volumes and surfaces compared to field sensor setups, which also quantify fluxes precisely and all water flux and water-dependent processes. The plant production needs to know when to irrigate and how much, and what is the current soil water situation, and so on. This webinar has 4 chapters, about 10 slides for the introduction showing the requirements for lysimeters, about 10 slides for the lysimeter techniques and the design. I'm showing 2 field examples, and finally about 10 slides for data management and data evaluation and data analysis. Maybe this is the most important step for users and should be taken into account when you plan to use lysimeters. Lysimeters are not only monitoring instruments, they actively control the water situation and therefore need a critical eye on what happens in the field and at the lysimeter. To a fifth chapter could have been the maintenance, which includes an at least weekly data check and at least 2 site visits a year for check of the system and the local situation. Now, this so-called Coshocton lysimeters installed about 75 years ago shows already important parts of a lysimeter. The container or vessel is mounted on a balance. Therefore, the container must have no force connection to the surrounding soil. A sealing is preferable to prevent air exchange or soil or other particles to get into the enclosure. Grease, oil or water covered with oil filled in a gutter can take up surrounding steel lip. Easier is a high flexible sealing material which is mounted to the lysimeter and the field enclosure. It is most important that this sealing has no interaction to the weight measurement. This slope lysimeter does not take into account lateral fluxes, which may be dominant at slopes, but it measures the runoff in a separate vessel, which is important for slope studies. It has a defined lower boundary, which is here 0. Water will flow to the drainage barrel without any potential. This point will be part of the following slides. The question is, how can we measure water fluxes in soils? Lysimeters do directly. How do they work? As you know, water always runs downwards. Why? It simply follows the gravimetric force due to its potential gradients. The amount of water follows the best possible path or flow paths or the water conductivity. How does water behave in soils? It does pretty the same, but in soil we cannot follow the non-visible water such easy as in rivers. But we can measure the potentials. Also in soil, the potential differences drive the flow. Those potentials can be measured precisely and directly only with modern pressure transducer tensiometers. Further, if plant roots want to consume soil water, they must suck with a much higher force than the holding potential. Irrigators therefore use tensiometers as the control of water by potentials gives them the direct water supply information. So let me proceed with a flip chart to illustrate what this means. This field setup is equipped with TDR probes, tensiometers, temperature probes and suction cups for the determination of water equation, covers the following requirements. Horizontal probe installation, which do not interfere with the main water flux. We install the sensing elements of the probes in the undisturbed soil profile. This disturbance has a far enough distance to the measure spots. For check and calibration issues, we have as easy access to the sensors with the access tubes. Logger, battery and sampling bottles for soil water samples are mounted in the service well for long-term monitoring services. To calculate the groundwater recharge capability and the evaporation rates, the Hydros 2D and other models are used. Therefore, we need the matrix potential differences, of course, in each layer and the according conductivities. The big advantage of this setup is not to influence the natural water fluxes. Typically, we need defined cross-section and defined lengths of flux measurement Typically, we need defined cross-section and defined lengths for flux measurement. The start and end point is determined by the so-called boundaries. While the upper boundary is given by the soil surface as interface to the atmosphere, we choose the lower boundary in the depths of the interested flux. This is usually below the root zone. To measure the weight, we further need an enclosure around the lysimeter vessel. Atmospheric interface means that we measure the mass of any kind of precipitation which gets on the plants or the soil surface from the lysimeter. This means the upper boundary is not the soil surface, but the plants as well. To ensure the water will remain on the lysimeter and no field water has access to the lysimeter, the upper edge of the lysimeter vessel and the ceiling are about 3 cm higher than the soil surface. Depending on soil texture, structure and moisture, the water starts to infiltrate more or less deep. In seasons with high precipitation, the water flux main direction is downwards and usually recharges the groundwater. High fluxes are observed at gravel soils, especially after hard rain events or snowmelt. Inside a gravimetric lysimeter, we have no flow path down to the groundwater layer. We use a filter bed to drain the free draining water. This means the metric potential at the lysimeter bottom is 0, which causes a capillary fringe above the bottom plate. This wet situation keeps the complete lysimeter wet compared to the field, where the water can follow the flow path potentially driven to the aquifer. The opposite situation follows in dry seasons. While the fluxes are oriented now upwards, the lysimeter has no connection to the groundwater and therefore gets drier than the field. The importance of this method depends on the soils, horizons, the distance to the groundwater level and the climate situation. Some lysimeter getting as dry that the shrinking gaps reach the bottom plate. Some climates have no typical dry season where rain provides water distributed all over the year. Some alpine sites, for example, have high amounts of rain pretty well distributed over the year. Some sites have deep groundwater layers. Here, the deeper soil horizons buffer the water deficits of shallow depths. Regarding the annual water balance, gravimetric lysimeters may accidentally correspond plus or minus to the field. This may be affected to the lower flux rates in wet seasons and lower evaporation rates in the dry seasons. Now, how do we reach field identical hydraulic situation fluxes inside of lysimeters? By having the identical metric potentials inside the lysimeters as in the field. So we compare those two potentials and keep them on the same level. How does it work? We need a field tensiometer and a lysimeter tensiometer at the same depth, fixed by the depth of the lysimeter bottom. We need to take off water from the lysimeter in the saturated but also in the unsaturated range. Therefore, we need suction cups or suction plates. While plates can clog due to sediment processes, it's preferable having suction cups mounted with a sedimental distance to the bottom plate. Further, suction cups work reliably over years, while plates need special care not to crack due to the heavy load or getting leak. We need a pump that drives the water from the lysimeter into a drainage barrel or back into the lysimeter. Sure, we need a drainage barrel. Its size fits to the amount of water needed to keep the lysimeter at field conditions as an artificial aquifer. And we need a pump controller which compares the two tensiometers and controls the pump. The drainage barrel needs further an emptying device like a siphon or a magnetic valve control. If the barrel is full, we reduce a defined amount of water back into the field below the lysimeter. With this, the natural flux situation got only a bypass, but the field balance is remaining. Sure, for measuring the drainage water amount, we measure the drainage tank with a balance too. The technical components and details are part of the next chapter, Technique. The technical requirements in general: high reliability, low maintaining effort, long-term life expectancy for long-term monitoring, waterproof due to field conditions, temperature-proof due to field conditions, easy to use and maintain, and finally, all measure techniques shall not influence the situation to be measured. This schematic view shows the technical components of a lysimeter with a cross-section of 1 square meter. In Smart Field Lysimeters, it looks pretty the same, but we measure the lysimeter matrix potential with a virtual tensiometer, as we take the pressure level directly in one of the 3 suction cups at the lysimeter bottom. The controller program takes into account the flux parameters and responses and the response speed of the field lysimeter. Important to say that the field lysimeter must be filled properly. If this is not the case, the controller activates a default modus which keeps the lysimeter weight on the latest level. The active surface of the porous suction cups or the suction cup rake are half of the lysimeter surface. In the Wagner project 2004, we tested if this is enough to even cover highest infiltration rates, which was the case, and no free drainage got below the suction cups to the free drainage outlet, which was provided to be on the safe side. Compared to big lysimeters, the suction cups at the Smart Field Lysimeters are suited in a bottom pan. The hydraulic contact to the soil is reached with a silica flour with high hydraulic conductivity in the range of 0 to -1 bar. You see the air reference port with the tubing connected to the pressure transducer at the right suction cup. The water tubings have low cross sections to prevent so-called dead volumes of water between the lysimeter and the drainage tank. The complete technical setup of a field lysimeter station has the following components. The picture shows a typical setup of a science lysimeter. Special here is the lysimeter vessel made of stainless steel, watertight sensor ports which allow the soil to move inside the lysimeter ±10 mm, sensors. The Smart Field Lysimeter has 3 ECO-TM probes for the water content and the water temperature. Further is equipped with 3 MPS2 sensors for measuring the matrix potentials. Those sensors are giving additional information inside the black box. Suction cups are no more part of the Smart Field Lysimeter. This is because of the removed sample water changed the hydraulic situation in this small lysimeter too much. So if a water sample from different depths are of interest, the cups should be installed in the field. Water permeable concrete for lysimeter to reach best temperature exchange is a part of the big lysimeters. Water impermeable concrete for the service well. To say the Smart Field Lysimeter has a steel cover which is responsible for good thermic exchange to the soil in the field. This photo shows the effort of an 18-channel field lysimeter setup with big lysimeters. For sure, the bigger a lysimeter is, the better the results are. But on the other hand, it requires heavy machines to set up the station and needs a long planning and much higher expenses. So the Smart Field Lysimeter is shown here in this picture. The following points make the Smart Field Lysimeter unique. The lysimeter cylinder, of course, is made again of stainless steel but with smooth surfaces to prevent friction during the excavation process. It has sensor ports in different depths depending on the complete depth of the lysimeter. It has a connector box for 7 sensors, for the 3 EcoTM sensors and for the matrix sensors and the tensiometer inside the lysimeter. So only 2 cables and the drainage tube leave the lysimeter at defined pathways for lowest interaction with the white measurement. The lysimeter bottom is made of stainless steel as well, with 3 high flux ceramic cups with a surface half of the lysimeter surface. Those are embedded in silica flour. The lysimeter weighing is used by the standard UMS precision load cells or balances PL50, PL100 or PL200, which take up a load for the 30 centimeter high lysimeters of 50 kilogram, the 60 centimeter high of a maximum of 100 kilogram, or the 1 meter high lysimeter can take up to 200 kilograms. The pressure cell itself is protected, is flood safe protected by IP68. So you install all lysimeter soil probes and the balance to 1 unit before you let it down into the lysimeter enclosure. The lysimeter enclosure has a steel barrel body that gives best thermal response to the surrounding soil. Its diameter is about only 450 millimeters, and a special shape epoxy collar with sealing to the barrel closes the enclosure on the top. It has a self-releasing sealing lip to the lysimeter for a minimum of white influence. The drainage field container has a dimension of about 1/2 meter by 1/2 meter and is about 1/2 meter deep. It's a ruggedized 60-liter polyurethane container and has a thermal insulated lid and 2 embedded side access ports. One goes to the lysimeter, which has a distance of only 1 meter. The other one is for the control cable to the data logger cabinet, which can be placed up to 50 meters away. The 10-liter drainage reservoir tank stands on another precision platform balance and has a siphon which empties the tank at the level of above 10 liters down to 8 liters automatically. The 8 liter remain as a reservoir for the dry seasons to keep the lysimeter moisture equal to field conditions. Also, a 5% sample bottle is filled each time the pump takes off drainage water from the lysimeter for analyzing issues of the drainage water. The provided overflow gets into the drainage tank. The bidirectional pump is located in the drainage field container inside a waterproof enclosure. This box connects the field tensiometer too, placed in this pump box too. So only one cable connects the drainage container to the logger cabinet, and on the side of the EC cable connects the lysimeter. The logger cabinet is now made of stainless steel, IP69 protection, and it's smart because of its smart dimensions of 40 by 40 centimeters. This is mounted on a stainless steel mast. The logger cabinet contains the DT80M data logger, the power management, pump controllers for each lysimeter, lightning protection, and a 26 ampere hour 12-volt battery. It is assembled with a small panel inside the door to facilitate the maintenance visits. Mast and lightning protection is prepared as well. We also supply the standard system together with a suitable 80-watt solar panels. For some application in low radiation situations, or if more than 1 lysimeters are connected, higher power panels are available. The data logger has an embedded GPRS modem to have a remote access to the station. Data can be uploaded automatically to a FTP server or web server, which can be pre-configured. If wanted, we can provide SIM cards, FTP server and additional services, for example, converting the data in monthly Excel files or PDF files. In future, we will offer several more value services. The lower hydraulic boundary control. All lysimeter cut the field water flux at the bottom plate. Gravimetric lysimeters with a filter bed have zero matrix potential, which is physically a groundwater level situation. Therefore, those lysimeters are, again, much too wet in rainy seasons, and the opposite happens in dry seasons where no capillary riser can come up from the aquifer, so lysimeters simply fall dry. This technique is designed with a completely new concept. The problem of regulation limitation to very wet conditions is now solved. The porous ceramic cups in the lysimeter bottom are tight over 1 bar suction, and therefore the boundary conditions can be regulated up to -850 millibars, which with very high accuracy and stability. The tension of the ceramic cups is measured and regulated and compared to the field T8 tensiometer. We call this a virtual tensiometer, since the tension at the ceramic surface is active, measured with a pressure transducer and logged as a data in addition to the matrix portion inside the lysimeter. Now, this concept is also modular, so the Smart Field Lysimeter system can take up 1, 2, 3 or 4 lysimeters with a depth of 300, 600 or 1000 millimeter. So if you decide to start with 1 lysimeter, you can easily connect up to 3 other lysimeters later with a single plug-in connector. Possible designs for more than 1 lysimeters are shown in the following slides. Depending on your needs or replicants, you may have 2 lysimeters with the same treatment. For sure, you can also have 2 different cultivations, or you can use a 4 lysimeter setup for climate change experiments. Here you see a photo of the Smart Field Lysimeter according with the sealing lip on the very top, the epoxy collar and which is removable to have access to the lysimeter and to the sensors, and with the field enclosure. Now let me show 2 examples of lysimeter setups in the Austrian and in the Italian Alps. The left photo shows the lysimeter tool set in action, which is an instrument we provide too. Dr. Georg Leitinger from the University of Innsbruck has made this setup about 1.5 years ago. The right photo shows a low impact after the field installation. The lysimeters work all year long, although they are installed at an altitude of 2,200 meters. These 2 pictures show the already suited lysimeters before we cover them with natural soil and grass. Those lysimeters are part of an irrigation project for climate change in the Italian Alps. Now, any instrument is only as good as the operator handles it. This means not only to maintain the system, but also to have an eye on what's happening in the field. What are the current conditions? How to check the data are correct? How to save data? And how to mark checked data? What to do with missing values? And how to mark data with additional nodes or field management? Those questions are part of the last chapter in this presentation. Regarding the data flux, you may have different locations and loggers sending different data. So for long-term monitoring tasks, a well-designed database is required. The data may get directly or onto a web server, which is in most of the cases a preferable solution. Anybody who has the access address is able to download and work with those data, but the initial data set keeps untouched. Also, the process of downloading the data from a logger is now standardized, so no mistakes happen anymore during handling in the field by downloading data. The data may get in by GPRS directly or by wire DSL and then to a FTP server. The standard should be a backup service. Next step is a pre-processing step to eliminate measured data from control data like checksum control parameters and status information like power voltage and so on. The pre-processing also eliminates data outside of technical range or generates no-value data out of analog status signals. After this step, we automatically generate PDF files to having a fast access on weekly, monthly or annual data graphs comparing identical or corresponding signals. The next step requires a data acquisition software for fast and comparable visualization of the data. The data engineer or technician has a careful look at the data while and evaluates them in accordance with the station, logbook or metadata like cameras or other control signals. With many data acquisition tools, some additional markers beside the data are possible. The marker may say, for example, A, which means checked by the engineer XYZ to be okay, or B, for example, snow cover, or a parameter C, which says maybe a virtualizing event, or D, the data are simply not verified. Further, the data engineer kicks off a report and a to-do list for the maintainer. In case of not verifiable, he tries to describe the failure reason and the maintenance handling instructions at the site. The next step is data processing, usually done by the scientist in charge. He decides if noisy data are really noisy or if this is an interesting phenomenon. He compares data on a deeper level to check if the data are plausible due to mathematic models or other scientific laws. Examples. These graphs compare several parameters. The upper graph compares tensiometer signals like red is the lysimeter tensiometer, the yellow blue and dark blue are field reference tensiometers. If the aim is that the lysimeter matrix potential is an average of field tensiometers, as it is here the case, we can say the lower boundary control is working properly. The next graph shows the comparison of lysimeter weight changes and drainage barrel weight. Sure, the lysimeter weight is also influenced by rain and evapotranspiration. So if we add the lysimeter weight and the drainage water, we get this information. Finally, the pump graph shows the history of pump runtime and direction. This is most correspond to the drainage amount. Finally, the protocol shows the station and time period. The next sheet shows the field manipulation and how does this affect the measured data. The upper graph shows, due to the weight reduction, samples have been taken out of the drainage tank. For sure, this can be modeled, but the model must be trained that these high degrees gradients are caused by an automatic empty process or by manually taken samples. The lower graph shows, again, weight of the lysimeters themselves. How to analyze data due to rain, evaporation and seepage water. Therefore, we add the drainage weight and the lysimeter weight in this graph in a first step. Generally spoken, a decrease of weight means loss of mass or loss of water due to evapotranspiration, versus increase of weight means addition of water to the lysimeter due to any kind of precipitation. If we then have a look only at the drainage weight, we know in the depths of the bottom plate the amount of water passes to the soil. This is the groundwater recharge amount if the bottom plate is deep enough. However, the higher the time resolution, the less it is a simple addition of losses and increases, because the signal noise would overestimate the results. On the other hand, rain does not start in hourly measure intervals, but rain starts in a minute and ends as fast. So the time interval for the white data should be 10 seconds to generate a 1 minute interval, average interval for data processing. Right now, we set up a group of lysimeter experts to work on an algorithm for rain and evapotranspiration out of the lysimeter weight data. This graph shows a typical water balance and mass balance of a tracer experiment we did for evaluating the lysimeter quality. The green graph shows the drainage amount over 2.5 years. At this site you see we have a peak from September 2005 to April 2006, which is a positive water balance, while in 2007 no drainage water occurred ever. There the water balance is 0, or what we expect it's negative. To the mass balance, we applied a tracer with a total of 38 grams. We found 24 grams in the vegetation, 9 grams in the leakage water, and 3 grams in the changed water content of the lysimeter. That's excellent. Finally speaking, lysimeters deliver high-resolution data on water, water flux, and mass transport with a field precision no other instrument does. Lysimeters work as high-precision rain gauges and evapotranspiration meters, as well as high-precision drainage measurement devices. Please have a look for more information on www.lysimeter.com, on www.lysimeter.at, on www.decagon.com or www.ums-muc.de. Finally, we are wishing you a nice winter and are looking forward to having you as a member in our Lysimeter family. Thank you for your attention.